Now we're going to discuss about the slip in induction motors through that slip derivations. We're going to derive the maximum torque achieved in induction motor. Okay. At the same time, what is the relationship between slip and torque in induction motor? What is the condition to achieve the maximum torque in induction motor? Okay. Then we are discussing about the characteristics of slip and torque relationship in induction motor. Okay. Then finally, we're going to discuss about losses and the efficiency of induction motor. Those are the topics. Now we're going to discuss about first, what is meant by slip? Okay, the term slip is suitable for induction motor only because in which which AC motor is not rotate the speed is not achieved induction or synchronous level. Okay, we all know. Okay, how can we calculate the synchronous speed? Ns equal to 120 F by P. The number of P is indicated as a number of poles. Okay, F is a frequency. So here the frequency and the poles is a constant means some AC motors is not achieve the synchronous speed. Okay, the main reason is okay. So through this explanation, clearly we can define difference between the synchronous speed and normal speed. That means actual speed of AC motor. Okay. Here, this is in this slip generally define difference between or variations of actual speed and synchronous speed. Otherwise, speed of revolving field and rotor speed. Usually, the slip is represented the symbol is yes, but it's always represented expressed in percentage. So percentage of slip is ns minus n divided by ns into 100. Here, n is nothing but rotor speed, n is synchronous speed. Okay, in some cases, the slip is defined difference between synchronous speed and rotor speed. Okay, it's a difference between 1 minus s into synchronous speed. This is a slip. Then, what is mean by slip speed? Slip speed is nothing but it is a difference between actual speed and synchronous speed. Here, the synchronous speed is always greater than actual speed. Okay, the value of slip varied depend upon the load. The load varies maybe 2% to 6%. Okay, in small motors, the percentage of load variation is a high. In large motor, the percentage of load variation is low. Okay, depend upon the load also, slip can be varied. Okay, here the torque and the slip relationship, the torque is directly proportional to flux and current, especially for rotor current, and also depend upon the rotor power factor. So in induction motor, the torque is dependent on flux, rotor current, and rotor power factor. The rotor reactance is varied slip because the rotor frequency Fr is equal to Sf. So the frequency varying automatically, it's directly proportional to the slip. Okay, once the frequency will be varying, the slip will be varying. The slip varying, the synchronous speed also varying. That is the main reason the normal induction motor is not rotated in synchronous speed. So the torque is directly proportional to slip and E2. Here E2 is indicated as a rotor induced EMF per phase. Okay, under standstill condition. Like that, X2 nothing but rotor reactance per phase under standstill condition. Okay, here the term K, the K is directly proportional to the torque. Okay, the torque is nothing but it is a proportionality constant. It's having a separate value. K is equal to 3 divided by 2 pi ns. Okay, what is the condition? How can we achieve the maximum torque in synchronous motor? Okay, when we need for maximum torque, the rotor resistance is equal to slip into rotor reactance. Already we know what is meant by X2. So in this condition, the maximum torque will be achieved. Slip is nothing but its ratio of secondary resistance and secondary reactance. Suppose both the values are equal, the slip is 1. Okay, we can clearly understand. So the maximum torque is independent of the rotor resistance because the maximum torque is directly proportional to the square of the induced EMF. Okay, that is nothing but it is a E2. Okay, so square of the induced EMF means E2 squared. At the same time, the maximum torque is inversely proportional to the rotor reactance. Okay, so the above equations clearly explain the maximum torque is depend upon two factor. One is a induced EMF, another one is a rotor reactance. Here, the maximum torque is directly proportional to square of induced EMF and inversely proportional to rotor reactance. Okay, then only through these maximum conditions only, okay, we have clarified that, okay, characteristics of slip torque. Here the slip value is varying from 1 to 0. Okay, depend upon this value we separate 3 regions. One is a stable region, another one is a unstable region, and the third one is a normal operating region. Okay, here first, okay, what is unstable region? Through this diagram itself, the B2T, okay, that point is indicated as a stable region. C2B is a unstable region. D2A is a normal operating region. Okay, these are the three separate regions are available in slip torque characteristics. Okay, in this stable region, slip value is very minimum. Okay, the above equations, T is equal to K into S into E2 squared into R2 divided by R2 squared plus SX2 squared. In this equation, the slip value is very minimum. So the slip value is very minimum is it's compared to the reactance. So the reactance value is very high. So SX2 is negligible. So we are considered only for R2 squared. In this condition, torque is directly proportional to slip. So the load increases, speed decreases, or slip increases. Depend upon the load, the slip value will be varying. In this case, load increases, slips also increases. So it's like a straight line. That means directly proportional. Suppose in the region is unstable. Okay, unstable slip value is maximum, SM. Okay, otherwise the slip value is here high. So in this condition, SX2 value is more. Compare the secondary resistance R2 squared. So R2 squared will be eliminated. We are considered only for SX2 whole squared. Numerator one S is available. Denominator S squared is available. So S and S will be cancelled. The denominator slip is present. In this condition, in unstable region condition, the torque is inversely proportional to the slip. So the torque is increasing depend upon the slip value. Slip value will be decreasing, the torque will be increasing for unstable region. Otherwise, slip increases, the torque decreases. This is look like a rectangular hyperbola. That is the indicator graph. B to C. Okay, that is look like a rectangular hyperbola. Normal operating region. In this region, the slip value is low, and the operating region's speed also very minimum. Okay, because at the time the speed value will be gradually reduced to reach the zero. The motor is operating in this region continuously. That's only this region name is a normal operating region. Okay, these are the slip torque characteristics. And the next topic is here losses and efficiency. Okay, in induction motor, various losses which will occur during the energy conversion. Okay, in these cases, we are considered for two losses. One is a constant loss, another one is a variable losses. Constant losses, the losses which are independent of the load and remains constant irrespectively. Load variations called constant losses. These constant losses, independent of the load, irrespective of the load variations, called constant losses. These losses is classified as core losses, friction, and windage losses. Okay, the core losses, it's in core losses again split up into one is a hysteresis losses and another one is a eddy current losses. Both are dependent upon the rotor core losses. Okay, the core losses, hysteresis, and eddy current losses. It's both are depend upon stator and rotor core only. Eddy current losses in rotor core is negligible. Rotor current frequency, because the rotor current frequency is very small. Okay, the frequency is 0.5 hertz to 2 hertz. So these losses are constant losses or fixed losses. Okay, mainly these losses depends upon voltage and frequency. So in these cases, voltage and frequency are constant. So those core losses are constant losses. Friction and windage losses, these losses depends upon the speed of induction motor. Almost the speed of induction motor is constant for normal running because the slip is very small. So these power losses due to the friction at the bearings and overcome wind resistance. So additional slipping induction losses occur in the slip induction motors also very minimum. Okay, so these kind of core losses, friction losses, and windage losses are constant losses. But variable losses, these losses depend upon the variation of load. Okay, for example, I squared R losses in stator and rotor winding. These losses occurs due to the resistance of stator and the rotor. Okay, at the same time, it's also present in copper. So copper loss also achieving, because here the losses is calculated. It's directly proportional to square of the current. Okay, other than that, contact loss also achieved. Here contact resistance is placed between the presses and the slip rings. Okay, constant resistance there. So its a magnitude is very small. So contact resistance is made be minimum. And third, one more important loss is stray losses. These losses are occurring in iron as well as copper winding of the machine. These stray losses cannot be determined exactly, but are accounted for when the efficiency of the machine is calculated by suitable factor. Okay, based upon the losses only, we will calculate the efficiency. Okay, the formula of efficiency is output power divided by input power. But usually the efficiency is to calculate in percentage. So output power divided by input power into 100. Okay, the input power is nothing but output power plus losses. Okay, these are the losses and the efficiency of induction motor. Thank you.